Hello everyone, I apologize for canceling class today. I almost never get sick, but while celebrating Easter with my kids at Myrtle Beach over the weekend, I got a little bit of a fever on Friday, and I've had a cough ever since. It's not COVID, unless the test is wrong. So I'm hoping my cough will mostly go away before Wednesday's lab, and I'll be back. In this lecture, I'm going to cover some announcements, review quiz 6, and then finish the material on real-time scheduling. So announcements, lab 4 was assigned last week, and the code is due Monday, April 25th, meaning you need to submit your code and designs by 11:59 p.m. on Monday, April 25th. That's next Monday. You can schedule demos outside of lab time if need be, up until the following Friday, April 29th, which is the day of the final. So please contact Phil to schedule a demo. If you can't find an agreeable time with Phil, then contact me and we'll make arrangements to meet. So again, lab is due this coming Monday, next Monday, and you can demo by the end of next Friday. Now I made some small changes to the lab sheet, nothing major, but I updated this H-bridge schematic diagram so we could relate it to the parts that we're using. So specifically, I added IA and IB, which are the two inputs to the H-bridge. I labeled those on these 4 switches. And then OA and OB, which are the outputs of the H-bridge, and M1 and M2, which are the inputs of the motor, are labeled here. So the M, of course, is the motor. OA and M1, for example, is the pathway from the H-bridge to the motor. And the inputs to the H-bridge, of course, are IA and IB, which are both pulse width modulated binary signals. I also made this H-bridge black on this schematic to make it a little easier to see, and I added a section on how to use the power supply in case anyone was having some trouble with that. The main point here is that when you program the voltage, or when you set up the voltage on the power supply, it does this thing where soon after you type in the voltage, it makes it 0, kind of zeroes it out. And the reason for that is because the power supply is constantly monitoring the voltage on its outputs. So after you get done programming it, after a few seconds, it reverts from back to the monitoring, and if the power supply isn't on, it goes back to 0. But after you type in 6 volts for channel 1, for example, it's in there, but you won't actually see it become 6 volts until you turn the power supply outputs on. So you turn the power supply on, but then to get it to energize the outputs, you have to then turn the outputs on. So that way, when you turn it on, if you have it hooked up to something, you don't risk blowing something up the minute you turn on the power supply. It's kind of a safety feature. Okay, so next announcement is quiz 7 is posted on Moodle, and it is due on Sunday night, this Sunday. It covers real-time scheduling. Also, someone brought to my attention that the syllabus had 3 exams listed, 2 midterms and 1 final. This is a holdover from when we taught this course virtually. We had no lab, so we had more time for exams. Obviously, this semester we were only having 2 exams, so I just redistributed the points. So the missing exam was worth 15% of the grade. So I just removed that, and I multiplied the other 4 components of the grade, namely the labs, the midterm, the quizzes, and the final. I multiplied each of their weights by 100 over 85 to just do an even redistribution. So now the programming assignments are 41.2, midterm is 17.65, quizzes are 17.65, and the final exam is 23.5. Also, I noted on the syllabus that the final would emphasize the material, the later material in the course, but that is no longer the case. The exam will, sort of equally treat all the material. It's a comprehensive exam. The final exam will be given on Moodle, and it opens at midnight on Friday, April 29th. That would be next Friday. And it closes at 11:59 p.m. the same day, so you only have one day to take it. Once you start the exam, you have 120 minutes to take it, and I expect there will be 25 questions on it. We will spend the next lecture, next Monday, reviewing for the exam. Okay, so let's switch to quiz 6, which was the quiz on control systems. So the first question is, which of the following is an LTI? Stands for linear time invariant system. Okay, there were 4 options here, and each of these are differential equations. Each of these differential equations have 2 time series variables f and g, and 3 of the 4 are not linear. Only this third one is linear. And the reason is because you can't, in a linear time invariant system, the variables can only be multiplied by a constant. So, in this first case, we're dividing them. Second case, we're multiplying, g, derivative of g times g. The fourth case here, we've got a g squared. Only this third case is linear. Which of the following is the S-domain form of f of t equals dg of t dt? So this is pretty straightforward. You capitalize excuse me, f and g, and t becomes s, and a derivative is translated to s times the variable of s. So f of s equals s g of s. Which of the following is a method for determining if a system is stable? First option is check if the order of the denominator polynomial of the transfer function is 2 or less. That's not true. The denominator order can be anything. But it does determine how many poles there are in the transfer function. But you could have a bunch of poles and it could still be stable, as long as all the poles have a negative real component. Option 2 is check if the numerator of the transfer function is non-zero. That doesn't make any sense at all. Check if any poles of the transfer function lie in the left-hand plane. If all of the poles are in the left-hand plane, then it's stable. But just checking if any poles are in the left-hand plane, not good enough. And the fourth option is the correct one. Check if the impulse response of the transfer function is bounded. Which of the following are valid eigenfunctions of the transfer function 1 over s squared minus s minus 56? So we factor the denominator to s minus 8 times s plus 7. And then we need to split the expression into 2 parts, where each of the part, which is a sum of 2 parts, I should say, where each part has a denominator that has an order 1 polynomial. So we're going to express this as a over s minus 8 plus s minus 8 plus b over s plus 7. So we need to solve for a and b. Little bit of a problem here because, we have two unknowns and one equation. But we can use this trick that doesn't always work. But in this case, I think it will. So we take the original expression, 1 over s minus 8 times s plus 7, and set it equal to the split version, a over s minus 8 plus b over s plus 7. And then we can create a common denominators by multiplying a times s plus 7 and b times s minus 8. This is just algebra. That allows us to eliminate all of the denominators on the left and right side of the equal sign because they're all equal. So that gives us 1 equals a times s plus 7 plus b times s minus 8. So yeah, what do we do now? Well, we could set s to be -7. If that's the case, then we end up with one equation and one unknown. 1 equals b times s minus 8 because one of the two terms on the right hand side is 0. And if that's the case, then b is -1 over 15. And then we can also consider if s is 8, in which case the right-hand term of the right-hand side of the original expression becomes 0. And we're left with 1 equals a times s plus 7, which we can solve as a equals 1/15. And so we can resubstitute in our values of a and b. And then we can do an inverse Fourier transform. And that gives us two eigenfunctions, which is 1/15 times e to the 8th power minus 1/15 times e to the -7t. Now, this transfer function is unstable because it has a pole at 8. And you can see that because, this function will grow infinitely as we increase t, but that's okay. What is the transfer function resulting from feeding the function 1 over s plus 1 into the function s over s squared? These are transfer functions, obviously. So we just multiply them. And so that gives us s over s plus 1 times s squared, or s over s to the 3rd plus s squared, or 1 over s squared plus s. You are designing a cyber-physical system to counteract the movement of a regular pendulum. For this, you need to model, and counteract meaning we want to stop it from swinging. For this, you need to model the physical system for your plant, which is the pendulum, whose angle is theta of t, and, because its angle changes with time. And the system input is a force, F of t. The time domain equation for the system is F of t plus d squared theta t dt squared, meaning the second derivative of theta with respect to time, equals minus b over m times d theta t dt, first derivative of theta, minus g over L times theta t. M is the mass, B is the friction, L is the length of the pendulum, and G is the acceleration of gravity, 9.8 meters per second squared. F of t is the force being applied, as I mentioned, and theta t is the angular position of the pendulum. What is the S-domain transfer function? Well, we got to convert it to the S-domain. So we can do that pretty easily because the second derivatives just get translated to s squared. First derivative translates to s. There's no integrals, and the linear terms are the terms that are not multiplied by any of the variables, or just stay as they are. Namely, negative b of m, negative g over l. And so the problem here is we need to get all the theta s's on one side of the equation and the f of s on the other side of the equation, because remember, our objective here is to solve for f of s over theta of s. So then we can factor out theta of s and then divide, oh, I'm sorry, excuse me. I reversed it. In this case, we want to calculate the transfer function of theta of s over f of s. So in this case, f of s is our input and theta of s is our output. So the denominator is the input, numerator is the output. So basically it's going to be a negative 1 over s squared plus b over m times s plus g over l. Okay, what is the S-domain transfer function of the PID controller with Kp equals 2, Kd equals 1, and Ki equals 4? 2 proportional by itself plus KdS, it's a derivative, in this case just as S, plus 4 over S, Ki over S, which gives us 4 over S, or 4S to the negative first power. We can restructure that as a function that has a denominator with an order of at least 1 by just multiplying this by S over S. Oh, yeah, which is, sorry, it's out of order. And what is the Tustin transform of transfer function f of s over y of s? Equals 1 over s squared plus 1 with t equals 1. T in this case is our sampling period, or our time step. So remember, when you do the Tustin transform, you just replace s with 2 over t, and since t is 1, it's just 2 times z minus 1 over z plus 1. So we make that substitution, and then you end up just working it through. Now, these can get a little involved when you do these Tustin transforms, but it ends up just being algebra. In this case, we ended up with z squared plus 2z plus 1 over 5z squared minus 6z plus 5. Okay, and what is the closed loop transfer function for the system below? So we have 3 LTIs with a reference. So the open loop transfer function is FGH, and the closed loop transfer function is the open loop transfer function divided by 1 plus the open loop transfer function. So it's just FGH over 1 plus FGH. What is the discrete time domain implementation of the transfer function f of z over g of z equals 2z plus 3 over z squared plus 3z plus 2? So I like these questions because with z domain, you can often convert these to time domain, which also gives you a code implementation for these, which is nice. Assuming, of course, that it's a linear system, linear transfer function. So the objective here is we have to get. Now remember, f is the output and g is the input. So you need f on f of t on the left side of the equation, and on the right side of the equation we want to have our g of t's, but we can also have some f of t's, or I should say f of z's rather, sorry. We can have some f of z's on the right-hand side. That's okay. So you might say, wait a second, like how can you have outputs on the right-hand side? Well, that's okay as long as the outputs are in the past. Obviously, they can't be from the future, and they can't be the present because we're calculating the present value. So that should be by itself on one side of the equation. So the first thing I did here was I wanted to get all of the exponents of z to be no more than 0, because z of 0 is the current value, current sample, and a z with a negative exponent represents previous samples, but we can't have any z's that have a positive exponent. So I multiplied this by z minus to the negative 2 power over z to the negative 2 power, and we end up with all our exponents now being 0 or less, and then took the denominator of the right-hand side and multiplied it against the left-hand side, and then I took the denominator of the left-hand side and multiplied against the right-hand side, and then you end up with f of z's and g of z's with coefficients, constant coefficients, and z's having, powers of 2 or less. And so we just need to get f of z on one side, it's our output, and our f of z's and g of z's on the other side, each of which multiplied by a z with a negative coefficient, which then allows us to translate those z to the negative power to be samples from the past, and then either input sample if it's multiplied against g of z, or an output sample if it's multiplied against f of z. So that's it for quiz 6. All right, so back to the topic from last week, real-time scheduling. Last week I introduced real-time scheduling / real-time systems. Basically, this is when you are designing a system that has to meet real-time constraints, which are in the form of deadlines for completing execution. I mentioned that the CPUs have a lot of uncertainty in terms of their worst case execution time because of a whole bunch of reasons. CPUs are not designed to be able to be predictable. That's because they have their memory systems are complex and unpredictable, as well as their interrupt systems, virtual memory systems, and so on. So some of you may have heard of a real-time operating system, and those do exist. No free ones that I know of. And they're all kind of a misnomer because it's very difficult to guarantee something is real time. However, you can make statistical guarantees. So we talked about that. So if you were to measure the worst case, if you were to measure the execution time of a task and sample those execution times, make multiple measurements, if you assume that these are taken from a Gaussian random variable rather, then you can come up with a worst case execution time, which is a certain number of standard deviations from the mean based on how confident you want to make your assertion that it's the worst case execution time. So we talked about that last time. I gave an example of that. And then I mentioned that one of the complications here is that in addition to the fact that it's difficult to know how long a task will take to execute on a CPU, you have this added complexity of having to have multiple tasks share a smaller number of physical CPUs, or maybe even just one CPU. And so, you end up with these tasks that can use the CPU, only one task at a time can use the CPU, while the other tasks have to, to wait. So, you could think of the task as having three states. It's either waiting to run, meaning it's ready, or it's asleep, meaning that it's already run, its work is done, or it's currently executing on the CPU. So for example, if we have 4 tasks with 4 different computation times, the assumption here is that these are worst case execution times is the computation time. These are listed in units of milliseconds. And then say we have a deadline for each one. Now this is assuming that we only need to run these tasks once, and we'll also assume that these are, for now, that these are non-preemptible, that once a task starts running, we'll run it till completion. So in this simple case, there's 4 tasks, so there's 4 factorial, different ways to, different orderings for running these to completion. And so I went ahead and did that, and show all 24. And so, you've got these diagrams where these are timing diagrams where if the task is running, it's shown as 1. If it's not running, it's 0. Of course, at any moment in time, only one task is running at most. And the red lines, these red lines are denoting the deadline for each one of these tasks. And so you can see in this first case, I ran task 4 first, then task 3, then task 2, then task 1. And you can see that task 4 made its deadline, as did task 3 and task 2, but task 1 missed its deadline because it was still running past its red mark. And that is actually ends up being the case, I think, for all 24 cases except for 2 or 3. So here's an example where they all make their deadline, where I ran task 4, then 3, then 1, then 2. And this is another example of an ordering that made its deadline. It was just 2 of them. 2 of 24 missed their deadlines. It turns out that the 2 that met their deadlines actually followed a policy of the first one is earliest deadline first. So you can see that task 3, which had its red line farthest to the left, meaning the earliest deadline, it ran first. And then the next furthest left red line was on task 4, so it ran next. And then we ran task 1 and then task 2. So earliest deadline first seems to work here. It actually, it always works as long as the total utilization is less than 100%. And then this other one, number 2, it also met this deadline, but it was following a policy of least slack first, where the slack is the difference between the deadline and the execution time. And so in this case, the task with the least amount of slack was 4 because it only had 17 milliseconds of slack. And so, even though, task 3 had the earliest deadline, task 4 had the least amount of slack. So that one worked. So from having fully enumerated this, I found these EDF, earliest deadline first, and ESF, LSF, least slack first. Those schemes worked. Okay, periodic scheduling algorithms are when you have a deadline for each task, but that deadline is also the period, meaning that after the deadline elapses, the task has to run again. And it has to run repeatedly on a period that's also its deadline. So it has to execute fully at least one time for every units of time specified by its period. So you can easily imagine how this is what you use to do control systems. So periodic scheduling is a little more tricky than what we had in the earlier case, where we only had to run each task once. With periodic scheduling algorithms, you usually assume that the tasks are preemptible, because this simplifies the scheduling, which means that if a task is running and another task's period elapses, or begins a new period, I should say, if that task who is beginning a new period has a higher priority than the task that's currently running, then that task will then run instead of the task that's running. And the task that's running, even though it may not have completed, is put to sleep temporarily. Excuse me. Assume, you have, in this case, we'll assume we have one CPU and a set of tasks. Each task has an execution time and a period, is denoted as T sub I, P sub I. Tasks can interrupt another task through preemption, as I mentioned. You want to find a schedule where no task misses its deadline, and for a given set of tasks, execution time or computation time and period, we can calculate that task set's utilization, which is the sum of the ratios of their execution time over their periods. Now, in this case, utilization is 1.5383, which would require more than one CPU to run, because basically it's 153% utilization. So we can't schedule this, but if you looked at this, you may not, it's not obvious until you calculate the utilization. All right, so we have two scheduling approaches, EDF, which I briefly mentioned already, and RMS, rate monotonic scheduling. Both of these schemes make a decision on which task should be running at any time. That decision is made under two circumstances. One, at the beginning of a period of any task, and also whenever any task finishes executing. The difference between these two is the way in which they prioritize tasks whenever one of those decisions has to happen. With EDF, it depends on which of the tasks has the earliest deadline. And RMS, it's just whichever task has the shortest period. Now you might think, wait a second, what's the difference? The task that has the earliest deadline may not be the task with the shortest period. And the reason for that is because the deadlines are relative to when the scheduling decision is being made, whereas the periods don't depend on when the scheduling decision is being made. In other words, the period is independent of the current time. Whereas the deadline depends on the current time. So what that means is that RMS has a fixed priority scheme. Every task has the same priority all throughout time, whereas with EDF, the priorities of tasks are constantly changing as time moves forward. So RMS is generally favored for that reason. So let's so take a look at the priority for earliest deadline first is, so if you have a task K, the priority is going to be its period minus the current time modulo the period, which is how far into the period we've gone, or that we're currently at. Okay, so that reprioritization has to be performed at a very fine granularity, meaning very often. However, the good news about EDF is that it's optimal, and it will always allow us to find a schedule as long as utilization is less than or equal to 1. In this case, we have 80% utilization with these 3 tasks, and we have the EDF schedule shown below. With rate monotonic scheduling, the priority is simply equal to the period. Obviously, in this case, lower numbers mean higher priority, but it may not be possible to schedule with RMS even if the utilization is less than or excuse me. But it may not be possible to schedule with RMS even if the utilization is less than 100%. So you can see in this case the RMS schedule and the EDF schedule for these 3 tasks, and with the RMS schedule we actually miss a deadline. Now I had to cheat a little bit, because using this task set with an 80% utilization and using RMS, it's scheduled. There's no problem. So I had to increase the utilization in this case to 98.3. And how did I do that? I changed the compute time and the period kind of across the board. But yeah, the RMS schedule misses a deadline, which is not too surprising because it's very close to 100% utilization. So how do we know if we can schedule with RMS? Well, there's a schedulability test. The test passes, we can guarantee schedulability with a given algorithm. If the test fails, it means we don't know. It might still be schedulable or it might not. We can't make any guarantees. So in the case of RMS, there's this schedulability test where you take each task and you add 1 to the ratio of its execution time over its period, and then you multiply those terms together. And if the product excuse me, is less than or equal to 2, then we can schedule. So for this task set down here, we do the test, which is we multiply 1 plus 10 over 40 times 1 plus 15 over 50 times 1 plus 5 over 20, which gives us 1.95. And that passes the test. This one is 1 plus 4/10 plus times 1 plus 3/12 times 1 plus 5/15. That gives us 2.33. That doesn't pass the test. Now, one thing you should keep in mind is that the RMS can actually achieve 100% utilization if the periods are mutually harmonic, meaning that any pair of periods is a harmonic. In this case, 20, 40, and 80 milliseconds. Okay, so the last topic here is how do we deal with multiprocessor scheduling? There's 2 approaches. There's partition scheduling, which is basically where you take your task set and each task goes to a specific processor, and then you treat that as a you treat the tasks assigned to each processor as a uniprocessor scheduling problem. You can do that, but then how do you assign tasks to processors? Because, if you have n tasks and m processors, there's m raised to the nth power ways to make that assignment. Another approach is global scheduling, where you allow any task to be assigned to any processor based on the edict given by the algorithm that you're using. So I have an example here for you. I found one global scheduling algorithm called rate monatomic first fit periodic scheduling. And so you assign a task to the first processor that passes the single CPU RMS schedulability test with the other tasks that are already assigned to it. So basically, this is a greedy algorithm where you just take the tasks in any order that you want to process them in, and for each one, you assign it to a processor based on whether it meets the RMS test, with the other tasks that have already been scheduled on that processor. So, is this any good? Well, it has a schedulability test, which is where you add up all of the ratios between execution time and period. And if that number is less than or equal to m, where m is the number of processors, times the square root of 2 minus 1, which is 0.41, then it'll schedule, which is not really that great, because that basically means that you're not going to get necessarily very high utilization of your processors. But that's a common problem in parallel computing. So let's look at an example. So if you just had one CPU and you had the following tasks shown in this table, the utilization there is 76.5%. And so if we do our single CPU RMS schedulability test, we would take 1 plus 2 17ths times 1 plus 2 19ths times 1 plus 5 21sts times 1 plus 7 23rds, and the product there is 1.9949. That's less than or equal to 2. So technically these would schedule on one CPU. Would they schedule on two? I mean, you'd hope, right? If it works on one, it should work on two. Well, let's find out. Well, the total utilization is 76.5, but if you take this 0.41 and multiply it by 2, you get 0.82. So yeah, I mean, it'll schedule on two CPUs. It kind of barely passes that, though. Let's look at another example. Let's say you have the task shown here. Utilization is 78%. If we do the single CPU schedulability test, we get 2.03, which means it fails. Again, that just means that we don't know if it'll schedule on one CPU. But on two CPUs, the utilization, being at 78, would have to be less than 0.82 for two CPUs. It means it is guaranteed to schedule on two CPUs. There is a form of earliest deadline first scheduling for multiprocessors as a global scheduling algorithm. Excuse me. So I have 5 tasks here labeled T1 through T5, and I'm also showing a timeline for two CPUs, which is currently empty. And these boxes represent the periods of the first of the task with the 3 lowest periods. I've got 2 tasks here with period 40 that don't fit on the slide. Okay, at time equals 0, we have all 5 tasks ready. The one that we will schedule first is the one with the earliest deadline, which is this red one, T3. The next one we'll schedule is the next highest priority, which is the green one here, T5. T5 finishes actually before T3, and when it does finish, we have T1, T2, and T4 ready. Now T1 and T4 are both the lower priority because they have the highest periods, and so T2, which is the blue one here, has, is the next highest priority, so we'll run T2. And then when T3 finishes on CPU 1, T1 and T4 are the only left. They both have the same priority, so we'll just pick one to run, so we'll pick T1. Now, T1 actually doesn't finish running because before it gets to finish, it's going to get preempted by the next period of T3, at which point T1 is, technically still ready. It was running actually, but now it's ready because we preempted it. But now we have T3 ready, and of course T4 is still waiting in the wings. So we're going to have to run T3. So T3 comes up, and then when T2, next milestone is when T2 stops running, or finishes, completes, I should say. We'll be left with T1 and T4 being ready. So we'll go ahead and run T1 because we were running it before. We'll allow it to finish. When T3 finishes, the only one that's ready is T4. So we'll run it, except it doesn't get to run for long because very soon afterward, T5 becomes ready. Because it starts its next period. Now the question is, do we preempt T4 or do we preempt T1? I gave T1 slightly higher priority earlier, so I'm going to assume that T1 still has higher priority. So instead of preempting T1, we'll preempt T4. And so, of the two, I'm going to preempt T4. So we'll run T5, which completes quickly. When it does complete, we have T4 is the only one left, so we'll run it. Well, we'll try to run it again, but it again gets preempted by the new period for T2, which, at that point in time, T2 and T4 are ready. So we'll run T2, and so on. So that's how global EDF scheduling works. You can tell how, you have to reevaluate priorities pretty frequently. So what are the schedulability conditions of global scheduling? The first one's pretty straightforward. The utilization has to be less than the number of processors, less than or equal to the number of processors, rather. The second condition is a little stranger, where you have to calculate the greatest common divisor of the periods of the task set. And then you assign that to a value, a variable t, and then for each of the ratios, for each task, you take the ratio of its execution time over its period, and you multiply it by t. And if for all the tasks, after you make that calculation, if that value is an integer, then the task set is schedulable. So for example, if you take this task set, we calculate the utilization, which is 24 over 40 plus 8 over 20 plus 4 over 10 plus 16 over 40 plus 3 over 15, which adds up to be 2, or 200% utilization. And we have two CPU. For two CPUs, it's for two CPUs that would be that would pass the first condition. The greatest common divisor of the periods is 5, and so then we take 5 times 24 over 40, 5 times 8 over 20, 5 times 4 over 10, 5 times 16 over 40, 5 times 3 over 15, and each of those turns out to be an integer. Sorry, I'm going to adjust that. So 3, 2, 2, 2, and 1. So that one's schedulable. Here's another example. See, what did we change? We changed the period of task 4, task 3, and the period of task 5. Okay, so we made a slight adjustment to 2 of the periods. In this case, utilization is still 2. The greatest common divisor of the periods is now 4. And so we do this calculation, and we end up with sum of the products between the greatest common divisor of the period and the ratio of execution time to period is not always an integer. So for task 1, 4 times 24 over 40 is 2.4. So that means that the schedulability test has failed for this set of tasks, which means that we can't guarantee that it's schedulable with EDF. So while EDF is optimal for one CPU, it's not optimal in the sense that it's not necessarily schedulable for multiple CPUs, as long, when the utilization is under the number of less than or equal to the number of CPUs. Excuse me. So that's all the material we have for this lecture. If you have any questions, let me know. I'm going to update the lecture slides on Moodle tonight. And if you have any questions, feel free to send me or Philip an email. Thank you.